I'm extremely happy to address the Large Charge seminar, and I want to thank the organizers for inviting me to it, and for also organizing all of these other Large Charge seminars that so many of you have spoken at that have been so nice. I think the first part of my talk is going to review some things which many of you probably, considering the subject of this seminar series, know already very well. But I'm gonna maybe give it a slightly different spin. Try to put it in as large, as broad a context as possible. Okay, so this talk, like probably many or most or all of the other talks in this seminar series, is about the simplification of strongly coupled quantum systems in the limit of large quantum number, which I will refer to generically as J. And by otherwise strongly coupled, I mean, outside of a perturbative regime. So where the theory becomes, outside of any regime where the theory becomes semi-classical for other reasons. Or maybe in a simplifying limit where there is a perturbative behavior for other reasons, but where the quantum number is taken so large that the system behaves differently than you might have expected, despite the system being weakly coupled. So even when there is a recoupling parameter, we might also want to take it weak, but scale the large quantum number large enough that it overcomes the weakness of the perturbative parameter and drives it into a qualitatively different regime. So the primary question in such a talk is this even a subject? And if so, why is it a subject? Well, the answer to that, I think probably all of you here know that yes, it is definitely a subject. In some sense, it's an old subject. Many examples have appeared in the literature going very far back into the past. And recently, there have been a number of groups. I see many people in the audience who've been involved in this and whose work, I should apologize, by the way, right away, that while I've given some of the older references, I'm still like a little bit, my references are still somewhat out of date. There's been an explosion of really fascinating work in this area, which in this talk isn't adequately covered yet. But many of you have been involved in sort of systematizing this point of view and applying it more broadly. So going back to the oldest references, probably the first paper in this on this subject was by Democritus, or the first papyrus or whatever they used back then. And actually already I noticed that I'm doing a bad job with the references. I think it was pointed out to me that Leucippus was co-discoverer of the atomic hypothesis, sometimes gets screwed out of credit by Democritus, so sorry about that. I will fix that. The correspondence principle due to Bohr, large spin limit in the hadron spectrum due to Regge, the macroscopic limit that was explored by Deutsch and Srednicki, and then the slightly more modern history starts with the BMN limit in n equals 4 super Yang-Mills by Bernstein, Melanson, and Nastase, and then large spin limit also in n equals 4 super Yang-Mills by many people, also Maldacena and Alday, but including many other people, Belitsky, Basok, Kurczewski, and Mueller. The large spin expansion in general CFT, where the focus began to shift to more generic stuff, starting with Komorgodski-Zhiboyev and also Fitzpatrick, Kaplan, Poland, and Simmons-Duffin, and then many papers by Aldi and collaborators. Then a large spin expansion in hadron systems was subleading corrections were also somewhat systematized by many groups, myself and Ian Swanson, with also Maida, Maltz, and Swanson, and then Karin Hewitt, Komorgodski, Sever, and Zhiboyev, and then further work by Sever and Zhiboyev. And then the more modern history starts maybe in 2015, where various people, maybe including many of you, started looking at large charge expansion in generic systems with abelian global symmetries, and also non-abelian global symmetries, charge and spin, topological charge, and then interesting EFT connections with bootstrap and large charge limit in gravity also. And also, I apologize, there have been, maybe in the last year, many very interesting papers on this same subject, including papers by Komorgodski, Paul, and Rajiv Moshe, and also papers on parity breaking, large charge EFT by Della Cratas, I'm sorry, Della Cratas et al. But many people, some of whom are in the audience. I'm sorry. Anyway, my references on this bit are not updated. Sorry about that. Vacuum manifolds and chiral rings at large R charge was explored by myself and others, including an interesting double scaling limit, which I was referring to obliquely in the beginning, where there is a perturbative parameter and the global charge is scaled to overcome the weak coupling, and then also non-supersymmetric versions of the double scaling limit were explored later on. Again, I'm sorry, my references here are sorely in need of updating, and that should be fixed, I notice. But by many people, including Russo and collaborators, and also by many excellent people in the EPFL school, Rattazzi, Cuomo, Badel, and so forth. And yes, people, anyone who knows that they should be included on this reference list, please actually email me or just message me in the chat. This is the first version I've given of this talk. References are out of date, sorry. But the goals of the large quantum number expansion are largely to answer the same questions as the conformal bootstrap, which is to say to learn to systematically and efficiently analyze QFT that have no exact solution in terms of explicit functions. We'd all like to know, what does theory space look like for generic theories and generic observables in those theories? And this is a very consequential question for field theory, mathematics, quantum gravity, and cosmology. Many theories are not integrable, and we need to learn how to attack them in general circumstances. So direct numerical bootstrap methods are remarkably efficient, being power law in the number of operators. But since the number of operators grows exponentially with dimension or central charge or whatever other quantum number, generally direct numerical attack is still intractable because of the exponential explosion of states. But interestingly, all known extreme limits appear to have simplifying behaviors in, I think, all known circumstances that we're aware of. This is somehow a generalization of the notion of duality. And in the case of large spin in a single plane, this limit has been analyzed within the bootstrap itself, the relative ease of which is related to the fact that the conformal blocks themselves carry the quantum number. For other quantum numbers other than spin in a single plane, this isn't the case. So I won't talk about this case because I don't understand it. But at the moment, there's certainly no known analytic bootstrap method to attack the case of even large spin in multiple planes for d greater than or equal to 4. So there's no sort of analog of standard large spin bootstrap for those sorts of limits. The same is true for various internal global symmetries. Although there was some, I think, progress um, that hasn't been adequately followed up on, I think, but should be, by Jafris, Muhammadjanov, and Jaboyev. Oops. So we'd like to translate EFT behavior into bootstrap terms, ideally. Ideally, we'd like to go further than that, but most modestly, we'd like to just translate EFT behavior into bootstrap terms and say what it means for CFT data, for operator dimensions and OBE coefficients. Maybe most grandiosely, we could derive EFT behavior from the bootstrap equations and use it to solve everything in every limit where direct numerical methods break down. And then maybe as an intermediate goal, one could use some small subset of EFT inputs and obtain some subset of CFT data not directly numerically accessible. So the grandiose goal is still out of reach. I've sort of tried periodically. There's been some very fascinating initial progress, I think, on the intermediate goal. But so for this talk, I'll talk about progress on the modest goal, mostly in detail about the supersymmetric case, but I'll talk about the non-supersymmetric case to begin with for context, for those of you who aren't familiar with it. The simplest example is the conformal Wilson-Fisher O2 model at large O2 charge, the critical conformal model. So the canonical question you can ask is, what is the dimension of the lowest operator at large O2 charge J? So translated via radial quantization, this is just the same thing as the energy of the lowest state of charge J on the unit two-sphere spatial slice. So a renormalization group analysis reveals the low-lying large charge sector is described by an EFT of a single compact scalar, which can be thought of as the phase variable of the complex scalar phi in the canonical UV completion of the O2 model. So the leading order Lagrangian of the EFT is remarkably simple. It's just some coefficient, which we don't know how to compute from first principles. We'll call it B. This is just the leading order Lagrangian, but there's only one unknown Wilson coefficient in it. So even this leading order Lagrangian has some powerful consequences. The consequence of the structure of the EFT is that the lowest operator dimension is a scalar of dimension that goes as j to the 3/2, where the coefficient is just some Sybil expression in terms of B, just some power law, some fractional power of B. Now, the leading order EFT, I think as many of you know and have studied and actually have made great contributions to, predicts more than just the leading power law, because quantum loop effects in the EFT are suppressed at large charge. So the EFT can be quantized as a weakly coupled effective action with effective loop counting parameter j to the -3/2. So for instance, we can compute the entire spectrum of low-lying excited primaries, as well as just the ground state. The dimensions and spins and degeneracies of the excited primaries are those of a Fock space with oscillators of spin L with L greater than or equal to 2. So the propagation speed of the chi field in the large charge background is equal to 1/√2 times the speed of light. We're talking here about dimension d equals 3. The speed of light is dimension dependent, but in a given dimension, it's universal and independent of the details of the underlying CFT. So the frequencies of the oscillators go as 1/√2 times root of L times L plus 1. Now, we said the primaries are given by the spectrum of oscillators with L greater than or equal to 2. The L equals 1 oscillator is also present, but exciting it only gives descendants. The leading order condition for a state to be primary is that there are no L equals 1 oscillators excited. So for instance, the first excited primary of charge J always has spin L equals 2 and dimension delta sub J plus root 3. And again, there's some generalization of this in higher dimensions, which was worked out by many people here. Subleading terms can be computed as well. So these depend on higher derivative terms in the effective action with powers of magnitude of the gradient of the scalar in the denominator. And these counterterms have a natural hierarchical organization in powers of the charge. So at any given order in derivatives, there's only a finite number of such terms. And as a result, at a given order in the large J expansion, only a finite number of these terms contribute. So since there are far more observables than effective terms, there are an infinite number of theory-independent relations among terms in the asymptotic expansions of various observables. So for instance, the gradient cube term is the only term allowed by the symmetries at order J to the 3 halves, but there is a one other term with a non-negative power of J, only one other, which we'll call, with a Wilson coefficient, we'll call B sub 1/2, times the combination magnitude grad chi times three-dimensional Ricci scalar plus 2 times grad of absolute value grad chi quantity squared over absolute value grad chi. And that relative coefficient between the two is fixed by the baryonic Weyl symmetry of the EFT, which is inherited from the Weyl symmetry of the underlying critical O2 model. So in particular, there are no terms in the EFT of order J to the 0, with the result that the J to the 0 term in the expansion of delta sub J is calculable, independent of the unknown coefficients in the effective Lagrangian. So specifically, the formula for delta sub J takes the form C sub 3 halves J to the 3 halves plus C sub 1/2 J to the 1/2 minus 0.0937256 and so on, up to terms vanishing at large J. And I should say this, the actual correct value of this, it's an important point of principle that this term is a universal and calculable, but of course it's still important to calculate it correctly, which was first done by in a paper by Alexander Monin. Anyway, and then there are further corrections vanishing with negative powers of J. So I think it's remarkable, by the way, that all this universal theory independent stuff is encoded in this very simple effective Lagrangian, which is really the absolute second simplest Lagrangian you could possibly write down, right? The simplest Lagrangian is Lagrangian for a free massless scalar, which is grad chi squared. Well, this is the second simplest, which is grad chi cubed. It really is just that simple. And it predicts all this interesting stuff, including this theory independent J to the 0 term here. So this universal term and the other universal large J relations don't have any fudge factors or adjustable parameters. Given the identification of the large charge universality class, these values and relations are universal and absolute. And similar predictions have been made for OPE coefficients by Monin, Pirchkalova, Vertazzi, and Seibold. And I should also say that there's an interesting generalization of this universal term to even dimensions, in particular 4 dimensions, was discovered by Gabriel Cuomo. Instead of a J to the 0 term, there's a universal coefficient of a log J term in the operator dimension, which is also theory independent. So many interesting structures were discovered in these sort of simple large charge EFTs, subsequent to what I'm describing. Um, so actually, I should stop and ask if there are any questions so far. I think many of you are kind of familiar with this earlier stuff, but any questions about that? Okay, well maybe I don't know. Maybe I'll skip over the frequently asked questions unless they come up. Um, maybe I should talk about well, there are other large charge universality classes, and in particular, supersymmetric theories with vacuum manifolds behave a bit differently. Um, so among the most tractable universality classes are these large charge universality classes with vacuum manifolds, because in these cases, the leading the lowest operators at large R charge are BPS, because they're chiral primary states. So first I'll describe the simplest case, which is occurs in n equals 2 superconformal theories in 3 space-time dimensions. The very simplest example has no gauge symmetry. It's just the superconformal fixed point of 3 chiral superfields with a superpotential XYZ. So its vacuum manifold has 3 one-complex dimensional branches, where one of the 3 fields is turned on. So you can just, for concreteness, consider the X branch. The other 2 are just permutations of it. The X branch has a coordinate ring spanned by the powers, just the simple powers, x to the j. And the BPS scalar chiral primary operators are the X branch part of the chiral ring of the theory. The dimension is exactly equal to the R charge and protected from all quantum corrections. So in this case, the formula for the dimension is kind of boring. It's just because these operators are chiral primaries, they saturate the BPS bound, and the dimension is just J in units where a free scalar has dimension and R charge 1/2. So we don't necessarily want to compute those operator dimensions. We'd like to compute something that's less boring. So the formula for the dimension of the second lowest primary, however, is also boring, because it's not chiral primary, but it lies in the another kind of special protected supermultiplet. It lies in what's called a scalar semi-short representation, which still doesn't have a full supermultiplet. So for these types of operators, the formula for the dimension is J plus 1. So that's also kind of boring, but nevertheless, we'd like to see this explicitly in a large J effective field theory. And we'd also like to be able to compute things like non-protected quantities, like the third lowest operator dimension, which is not BPS. So the effective theory describing the lowest state is just the moduli space effective action. So for all the supersymmetric examples, the moduli space effective action describes the large R charge EFT. It plays the same role as the gradient cubed theory for the O2 model, because the magnitude of the field is now in the same multiplet as the conformal Goldstone, so it's in the EFT as well. That's the main difference. So another difference is, unlike the O2 model, here the leading effective action is just free. So there are some higher derivative D terms, but the leading action is just this this thing, this free action, where we've written an approximately free chiral superfield as a fractional power of the X branch field. So to compute operator dimensions, we just quantize the theory on the round sphere. And now we have another of these classical solutions that we quantize the theory in the background of. And so here, the frequency of the solution, the helical frequency, is just determined by supersymmetry, by the BPS bound, rather than by unknown coefficients in the Lagrangian. So the results of the direct diagrammatic quantization are as follows. So one can really do a direct sort of superspace computation and compute the second and third lowest states. So as well as the lowest. So for the first and second lowest, of course, these are going to be determined by supersymmetry, but we want to do an explicit check to make sure that our action and the quantization of it are okay. So what we find from a direct quantization is that the lowest operator dimension goes as 0 times j to the 0 plus 0 times sorry, j plus 0 times j to the 0 plus 0 times j to the minus 1 plus 0 times j to the minus 2 plus 0 times j to the minus 4. And of course, we expect the other coefficients to be 0, but that goes up to 3 loops, which starts getting hard to check. Then for the second lowest, the thing that should be a scalar semi-short, you can check explicitly that the operator dimension goes as j plus 1 plus 0 times j to the minus 1 plus 0 times j to the minus 2 plus 0 times j to the minus 3, again, with a 2-loop correction that one didn't actually compute, but presumably also vanishes, confirming the predictions of supersymmetry to the order we can calculate. The third lowest primary is a non-BPS scalar, so we expect something finally interesting to happen here. And the dimension here is j plus 2 plus 0 times j to the minus 1 plus 0 times j to the minus 2 minus kappa times 192 pi squared times j to the minus 3 plus higher corrections, where kappa is the coefficient of the leading interaction term in the EFT. So the form of the leading interaction term is a D term consisting of a 4-derivative bosonic component, also plus fermionic terms and curvature corrections, which are important for the actual computation. And fortunately, we didn't have to compute those terms. Those completing terms were worked out quite recently by Kuzenko. The supersymmetric completion, which completed the conformal completion by earlier authors. Now, we don't know the value of kappa, again, for the XYZ model. It's a free Wilson coefficient, as far as we understand. We do know its sign, which is positive. So we know that the first non-protected operator dimension gets a contribution of order j to the minus 3 with a negative coefficient of unknown magnitude. Now, it's more fun to compute quantities which are both non-trivial in the large J expansion and checkable in principle by exact supersymmetric methods. So one nice example is the 2-point functions of chiral primary operators in 8 supercharge theories. And the technically simplest class of those, much technically simpler than other things you could do, are the Coulomb branch chiral primaries in 4-dimensional n equals 2 theories in the special case where the gauge group is rank 1, so SU2 or SO3 gauge group. So examples are n equals 4 super Yang-Mills, super conformal SU2 super QCD with 4 doublets in the fundamental rep. And then there are also many non-Lagrangian Argyros-Douglas theories with 1-dimensional Coulomb branch, including some n equals 3 examples. So some of these examples are Lagrangian, some are non-Lagrangian, but it's interesting that you can make a prediction that treats them all on equal footing. So let me say what that is now. So the Coulomb branch chiral ring in a rank 1 theory is spanned by powers of the chiral ring generator, which has dimension delta, so the nth powers of the chiral ring generator, where the generator of the chiral ring has U1R charge J equals delta. And by the way, I'm normalizing the R charge with a factor of 2 differently from basically every other author in the literature. Sorry about that, but it was convenient for us. At large charge in radial quantization, these correspond to classical solutions on the sphere again, where the Coulomb branch scalar gets a VEV proportional to root J over the radius of the sphere. So for Lagrangian theories, the generator is just phi squared. In Lagrangian theories, the dimension of the generator can take other values, which are constrained to some extent by supersymmetry, but they can take many interesting rational values between 1 and 2. So we can write the large J effective action in terms of an effective field, which canonicalizes the dimension of the scalar. And the singularity is irrelevant for all power law corrections at large J, and even some exponential corrections too. So the leading order action, again, is the free action. And the leading order interaction term is given by an anomaly term, a sort of Wess-Zumino term for the Weyl A anomaly, and for the U1 R charge anomalies related to it by supersymmetry. So the leading interaction term, this anomaly term, can be written as a D term, but it's really an F term. So you notice that it's convenient to write it as a D term, which helps work out the component form of it. But it's a D term of a non-single valued quantity. So it's not really a D term. That's why it's under control supersymmetrically. It's really kind of secretly an F term. Its single valued form is written as an F term. And then there's a superconformal completion, which was partially worked out in the literature, and we had to partially work out the rest ourselves. And then this coefficient alpha is proportional to the Weyl anomaly mismatch between the A coefficients of the underlying CFT and that of the EFT of a single vector multiplet, and possibly some massless hypermultiplets as well, depending on the theory. So some comments on the interaction term. It was first written by Dine and Seiberg in 1997. It's formally, again, a D term, but not really a D term. And its bosonic content is just the non, well, the full bosonic content is the bosonic content involving only the scalar is the Wess-Zumino term for the A anomaly that was used to prove the A theorem in 4 dimensions. And that's why this coefficient alpha is proportional to the A anomaly mismatch. Another remarkable fact about rank 1 theories is that the anomaly term is the only F term on conformally flat space. All other F terms for rank 1 theories are proportional to powers of the Weyl curvature multiplet. So, and all of our computations are going to take place on conformally flat space. So it's really an extremely simple effective theory if you're only computing a supersymmetrically protected quantities. So of course there are many higher derivative D terms, but those contribute to chiral primary correlation functions. Okay, so the EFT therefore has this very simple form. It's a free kinetic term for the vector multiplet, an anomaly term, and then some higher D terms, which we don't need to know because they don't contribute to anything. For quantities insensitive to D terms, this first 2 terms of the effective action can just be quantized meaningfully and gives unambiguous answers to all orders in large charge perturbation theory. So the dimension of the generator of the chiral ring doesn't enter into the EFT at all, nor does the marginal coupling or any other parameter. So in other words, any purely F term dependent observable has a large J expansion that's uniquely determined by the anomaly coefficient alpha and not by anything else for a one-dimensional Coulomb branch n equals 2 superconformal gauge theory. So questions on that in principle? Because now I'm going to just, I'm not going to keep justifying those facts. I'm just going to use them to prove and to calculate some things. So one set of observables of supersymmetrically protected D-term insensitive observables are the Coulomb branch correlation functions, which, so they're not quite the unnormalized correlation functions. They are the unnormalized correlation functions, meaning you can think of them as a partition function for a path integral with sources. So they're equal to the sphere partition function without insertions times the normalized correlator, also times a factor just soaking up the trivial conformal scaling behavior of the 2-point function. So right, this can be thought of as a partition function with sources, a path integral of the EFT action, and a source action where the source action is just the negative of the logarithm of the insertions. So this e to the q sub n, or z to the n, is this unnormalized partition function. That's going to be important towards the end, when we talk about some scheme dependent quantities. So right, these quantities are scheme dependent and also dependent on the normalization of the chiral ring generator, but those dependencies cancel out when you consider the double differences of the q's, or these funny ratios of the z's. So the exponential of the double difference of the q's, all scheme dependencies cancel in these quantities, and they can be translated straightforwardly into manifestly scheme independent quantities like OBE data. So now these can in principle be evaluated straightforwardly as functions of J and alpha using Feynman diagrams. Oops, misspelled Feynman there, sorry. That R is not supposed to be there. With no further input from the underlying CFT, as long as we are in large R charge perturbation theory. So the form of the expansion is Qn is equal to plus B plus J log J plus some quantities, the linear and constant terms in the expansion. The third term is the classical value of the source term and the one loop free term and classical anomaly term contributions here. So the last is the series of power law corrections coming from loop diagrams, with interaction vertices coming from the source term and the anomaly term, with the anomaly term vertices carrying powers of A, and the source term carrying powers of log J. So the structure of the EFT makes the polynomials k hat sub m a polynomial in alpha of order m plus 1. We don't know what it is yet, but we're about to find out. So in principle, again, you could just calculate all of these from directly by calculating Feynman diagrams, and the structure of the Feynman diagrams would be like this. And the little blue vertices are powers of alpha. So each blue vertex comes from the vertex with the anomaly term. The other vertices come from the source term. And of course, the propagators come from the free Lagrangian. Now, directly evaluating multi-loop diagrams in an EFT is hard, especially on a curved background. So to evaluate the power law corrections, we didn't, for the most part, we didn't compute Feynman diagrams. In particular, we did compute this Feynman diagram, and we were able to infer the others by a series of tricks. So we evaluated the tree diagrams directly, then used some known data for theories like the free vector multiplet and n equals 4 super Yang-Mills. Then we used the supersymmetric recursion relations, which I'll say a bit more about soon, and used the embedding of the Coulomb branch EFT into various sort of non-unitary but superconformal regulators involving ghost hypers to apply the recursion relations for arbitrary values of alpha, even when unitary Lagrangian theories don't exist. So with this combination of tricks, you can solve all the power law corrections for any value of alpha, with the result q sub n is an plus b plus log of gamma of j of alpha plus 1, plus exponentially small corrections. And I'll comment on those exponentially small corrections in a moment. This is, I think, some of the more interesting recent stuff that we've learned. So, well, I don't have too much time, so I'm going to skip actually over some of the evidence for the correctness of the large J expansion in the non-supersymmetric cases. But I will say that uh, for the non-supersymmetric large charge EFT, these universal predictions were verified to extremely high accuracy using Monte Carlo data and also various large N techniques and so on. There's also been highly accurate prediction agreement with Bootstrap to the extent Bootstrap is able to compute things, which it is for J equals 2, not so much for higher charge, but so I think this sort of thing inspired us to try to see how far we could push the precision agreement for supersymmetric correlators at large R charge, where there are tools for checking things to high precision. So let's move on to these predictions for superconformal correlators. So for n equals 4, the prediction of the gamma function is verified exactly. There are no exponentially small corrections to the formula. For other cases, the correlation functions can be evaluated by exact supersymmetric methods. Though at present, those methods are limited to theories with a marginal coupling. It would be great if, for instance, there were bootstrap data, which there are in some cases, but for some low values of the R charge, but high R charge bootstrap data to compare with. There isn't yet, but hopefully someday. So in 2018, we were able to find some extremely enticing preliminary precise agreement of the formula with localization methods in n equals 2 super QCD with 4 hypers, comparing double differences with the gamma function. But I think, and the agreement was so good, we thought it would be interesting to try to understand the exponentially small corrections, because at this point it was clear that the leading disagreement was one of these exponentially small terms. So the natural candidate for such an effect would be the propagation of a massive particle over the infrared scale. So we'd expect the leading difference between the localization result and the EFT prediction to be something like a constant, or maybe a power law, or something like that, times the exponential of a constant times root j over m tau, because the mass of an electrically charged massive state, a massive BPS state, has this kind of dependence, at least at weak coupling. And I'll be a bit more precise about that soon. And we found a pretty precise fit in the, especially in this double scaling limit, where J is taken large and the coupling is taken weak in some fixed ratio, so that this double scaled coupling lambda stays fixed. We found extremely precise agreement with an exponential ansatz corresponding to the mass of an electrically charged particle. But we still didn't have, I think, real theoretical control over the exponent. In fact, I think the early guess we made for the exponent was not quite right. But it's a rather interesting situation, I think, due to the magic of supersymmetry. Not only can we compute all power law corrections exactly, modulo the scheme-dependent coefficients, we're actually able to compare exact results to a precision where we can see the qualitative breakdown of the effective theory that we used to generate the all orders approximation. So seeing this, one is naturally tempted to try and go further and compare the exponentially small correction with physical expectations at a precision level as well. So in order to do this, one has to take the non-super universal, non-universal whatever, but I guess by super universal I mean things that aren't that depend on the on the CFT. Don't even depend on the CFT, just on the large charge universality class. We need to sort of take on solving for A and B. The sum rules are fine for checking power law corrections, where all the three adjacent terms have roughly the same order of magnitude. But when you're talking about exponentially small corrections, which are rapidly decreasing as a function of n, the sum rule tends to introduce large relative errors. And one would like to do better than that. And so to do that, we had to derive the actual value of the coefficients A and B, which we did in a series of papers over the last couple of years. So the main challenge in doing this is that the A and B coefficients are not only dependent on the marginal parameters, they're also scheme dependent. So often in the literature, including on supersymmetric localization, people use scheme dependent to mean to almost be synonymous with inherently ambiguous, but that's not really right. That's actually wrong. And you can say some things about scheme dependent coefficients. You just have to be careful about how operationally you're defining your renormalized Lagrangian parameters relative to whatever UV completion or renormalization procedure is being used. And with a little bit of care, one can actually solve for these A and B coefficients. So for generic theories with marginal parameters, it's a bit involved to do that. But for theories with extended supersymmetry, the scheme dependence can often be reduced to an ambiguity by a holomorphic function of the complex coupling constant. And for theories like SQCD, which has an S-duality symmetry, even the holomorphic ambiguity can be reduced to a finite parameter, which can then be eliminated altogether by matching with perturbation theory. So that's the course we took. So the first scheme dependence to discuss is the one that affects the A coefficient. It's a kind of classical scheme dependence having to do with the parameterization of the holomorphic gauge coupling. It doesn't have anything to do with it's independent of the sort of quantum mechanical regularization of things. The Coulomb branch chiral primary trace phi squared is uniquely defined up to an overall normalization characterized by its supersymmetry properties and by its dimension and R charge. But the overall normalization is exactly what matters for the A coefficient. So we have to specify it. So in the literature, the way that's mostly used to normalize curly O is by its relationship to a marginal operator. So curly O can be thought of as the n equals 2 f term superspace integrand over all four positively R-charged Grossman coordinates to generate the holomorphic half of the marginal operator that adjusts the gauge coupling tau. So the self-dual part of the field strength squared and its supersymmetric completion enters with some normalization, some fixed normalization relative to the superspace integrand. So the normalization of curly O is related to which is the chiral primary, is related to the normalization of the two-dimensional, this should be curly M, the marginal operator, excuse me, is related to the dimension of the chiral primary curly O. That's a superconformal descendant in the same multiple. But this doesn't resolve the question because a marginal operator doesn't have a universal natural normalization either. So a marginal operator transforms under reparameterizations of the coupling constant as a section of the holomorphic cotangent bundle of theory space. So if curly M is the holomorphic half of the marginal operator, it transforms like this. Curly M defined in the coordinate tau is the Jacobian del tau over del tau, del tau prime over del tau times the marginal operator relative to the holomorphic coordinate tau prime. And the chiral primary curly O has the same transformation, since its normalization is canonically related to the normalization of curly M. So under this coupling reparameterization scheme transformation, the exponentiated A coefficient transforms as the norm squared of the chiral primary itself. So it's the same sort of transformation, but with a square of a norm square of the Jacobian instead of just the holomorphic Jacobian. So the exponentiated A coefficient transforms that way. And we can exploit that transformation law to solve for A in a particularly simple holomorphic coordinate, and then transform it to whatever other holomorphic coordinate we like. So there's a second, less obvious scheme ambiguity related to the Euler density counterterm E4, which was first noted by Gomis and Gertkovitz in 2014. It's very non-obvious why this counterterm should even be relevant at all for the computation of two-point functions, but some elementary deduction shows that it is. After all, two-point functions on flat space are conformally equivalent to two-point functions on the sphere, and the four-sphere has non-zero Euler number. So it's clear that this counterterm has to enter into the unnormalized correlators. The sphere partition function transforms multiplicatively under an additive shift of the coefficient of the Euler counterterm. So supersymmetry does allow this counterterm to enter, but it's constrained, its coefficient is constrained to be holomorphic and anti-holomorphic, plus anti-holomorphic as a coefficient of the gauge coupling. So since the z sub n, or e to the q sub n, are unnormalized partition functions with sources, they have the exact same counterterm ambiguity as the sphere partition function without sources. So that means that e to the b transforms the same way as the Euler counterterm ambiguity in the sphere partition function. So the sphere partition function and e to the b both transform with norm squared of a holomorphic function under this ambiguity. So that means we have to assign b a scheme label as well. But again, we can do that. And fixing these ambiguities is greatly simplified in a theory with an S duality. So in terms of the exponentiated coupling, e to the 2 pi I tau, the S duality symmetry acts as, well, the S generator acts as q to the 1 minus q, the T generator acts as q to q over q minus 1. This isn't quite the familiar transformation of the coupling in, for instance, n equals 4. The familiar transformation is sigma. So sigma is the effective abelian gauge coupling, and that does transform this way under SL2Z, with the generators acting by sigma goes to -1 over sigma, and T sigma goes to sigma plus 1. And the relationship between the two couplings is given by this modular lambda function, which has an additive shift and a series of instanton corrections. So given our transformation law for coupling reparameterizations, we can take modular transformations as a special case. So it follows that the chiral marginal operator, curly m, and the chiral primary transform as holomorphic modular forms of weight 2. So the exponentiated a coefficient has to transform as a non-holomorphic modular form of weights 2, 2. The next ingredient is the recursion relation, the Papadinimus relation, which was a generalization of the TT star equations to d equals 4. And the recursion relation is this. It's well, it's just like that. So when applied to the power law corrections, they uniquely fix the form of q sub n to be this gamma function up to the linear and constant term. But they also give equations for the coupling dependence of the a and b terms. So for the a function, they say that the a function has to satisfy what is exactly a Liouville equation. And then for the b function, they just say that the difference between a and b has to be holomorphic plus anti-holomorphic. And notice that these equations are covariant under both scheme transformations. So that means we can solve these equations in any scheme we like and transform it to whatever other scheme we like. So it's simplest to solve in the sigma coordinate. And in the sigma coordinate, the Liouville equation, the modular property, and then matching with leading order of double-scaled perturbation theory, uniquely fix the result to be e to the a in the sigma frame is 16 over m sigma squared. So very simple expression in the sigma frame. Now, to specify the Euler counterterm scheme, we'll just compare with the scheme in which the partition function was originally calculated by Peston using the U2 instanton partition function computed by Nekrasov. And in that scheme, the partition function has a particular duality transformation. So it transforms under the S and T generators with these particular holomorphically factorized transformation laws. And I should say this can be derived. It wasn't in the literature. It doesn't appear as far as we know. And in order to find it, we had to relate to a slightly different scheme used by Alde, Gayoto, and Tachikawa, where the transformation of the 4-point function is in Liouville theory is related to the duality transformation of the sphere partition function. So with this transformation law, we can also solve for the B coefficient in the Peston-Nekrasov scheme, and it's this sort of funny-looking but rather concrete expression in terms of modular lambda functions and Dedekind eta functions, and also the 1 over m tau squared. So we could solve that up to an overall coefficient, and then again the overall coefficient we could find by matching again with double-scaled perturbation theory using the one-loop solution and its exact dependence on the double-scaled coupling found by Grassi, Komargodski, and Taizano using matrix model methods. So with that matching of the one overall parameter, we were able to find the absolute normalization of the B coefficient as well. Okay, so and then finally there are the exponentially small corrections, and this is by far too much detail to go into, but the summary is that one can just solve for the exponentially small corrections in an asymptotic series using the exact same strategy, using the recursion relations and to give differential equations for the order by order expansion of the exponentially small corrections, and then fixing the integration coefficients by matching with the Grassi, Komargodski, Taizano solution to one-loop double-scaled perturbation theory. We were able to fix all undetermined coefficients order by order in the large charge expansion of the exponentially small correction as well. So since we're out of time, I'll just show you the plots, and let me remark on something about these plots. So the biggest challenge we've had in discussing these very precise agreements between large charge expansion and exact results has been plotting the results in a way that shows the errors in a way that are visible to the naked eye. So so we plotted these in a kind of weird way. Instead of plotting the actual theory and exact results together, we've just plotted the difference between the two, and not even the difference, but the log of the difference relative to the log relative to the size of the exponentially small correction itself. So we take the exponentially small correction as determined by localization, subtracting the EFT result. Then we subtract the large R charge estimate to whatever order of approximation from that, divide by the value of the exponentially small correction as determined from localization. Take the log of that, multiply by -1 over log 10 to get the number of agreements, the number of significant digits to which the large charge estimate for the EFT approximation, the large charge estimate for the exponentially small correction agrees with data. And so you can see here, this is the leading order, next to leading order, next to leading order, next to leading order, and so on up to next to the 6th leading order approximation to the exponentially small correction. This axis is the number of significant digits to which it agrees with the result from localization. By which I mean the number of significant digits to which it agrees with the exponentially small correction as computed from localization, not the exact result. The exact result has 7 to 9 more digits of precision. So, but you can see for the next to next to next to next to next to next to leading order correction, we have more than eight significant digits of agreement. This is for the fixed coupling large charge approximation. We can also do the double scaled large charge approximation, which has slightly different properties. It oscillates about the exact result. So it has more of these accidental agreements, which look like little spikes on this logarithmic way of describing the agreement. But you can see that we get, again, about 8 digits of accuracy. So I think that's all I have time for, but I want to end by just talking about some of the sort of conceptual implications for the way we think about the relationship between microscopic and macroscopic phenomena in physics. Phil Anderson was famous for advocating that we just think of the microscopic and macroscopic worlds as two separate worlds without any real relationship to each other. He summarized this with the slogan "More is different." But we can see here that there's a very tight connection between the microscopic and macroscopic worlds. But moreover, what's I think really striking, especially if one goes back to the non-supersymmetric examples where we can see more clearly, I think what's really striking is the level of agreement between the level of agreement between the macroscopic approximation, this large charge approximation, and exact results, even at small charge. So it's a sort of inversion of the way, as theoretical physicists, we often think of things. We often think of the microscopic approximation, the microscopic formulation of a theory as being the fundamental one, with macroscopic limits being a sort of crude approximation which loses lots of information. Then Anderson said you shouldn't even think of it as an approximation, you should just think of it as some separate thing. But what emerges here, I think, is that you can really use the macroscopic approximation as a surprisingly accurate approximation, even for what we would think of as microscopic phenomena involving low quantum numbers. And one has these extremely accurate results for that. And when higher orders of perturbation theory and exponentially small corrections are taken into account, one really has the macroscopic approximation as a practical tool to study not only large quantum number phenomena, but even small, low quantum number phenomena. You can see here, one has accuracy of about 1 part in a million, even for our charge of 5 or 10. And that's even without adding in higher orders of approximation. One just sort of stops here because the computation starts getting a little bit complicated. Anyway, so I guess I'll end there and take questions. Thank you very much.
Okay, so thank you very much. And other questions, comments? Just feel free to unmute yourself and go on.
Simeon, what are the prospects for doing these sorts of things, but not at rank 1?
Oh, yeah, this is a great question. So you're really the person who would know best. I think that I think the prospects are good. The technical issue which is involved has to do with classification of superconformal higher derivative f terms for rank greater than 1. So certainly they do exist.
Right.
And understanding what things are computable and what things depend on the EFT Lagrangian at which order depends on classifying those terms. Now, even when those terms exist and affect a correlator, because they're F terms, there is probably some sort of like higher derivative Seiberg-Witten theory by which one could, solve for some of those F terms. Optimistically, maybe even, all of them in some cases. And
But-
so you, as you know, were the pioneer in classifying many of these higher derivative F terms. And I think, with the additional restriction of superconformal symmetry, it may be that they're restricted enough to make it tractable to do higher rank. But at the moment, that's the technical thing that one needs to do.
I guess I'm confused as to why looking at these higher derivative F terms is enough. There'll be all these higher derivative D terms as you go up in rank, and they're just going to explode. Why won't
But the D terms don't affect these correlators.
I see.
But these are supersymmetrically protected, so they're D term insensitive. So I think knowing the F terms would be enough, and even knowing something about them, can get you some partial information like sum rules and so on. That could be compared with localization data and so on. So yeah, even partial information about them would be very interesting and very useful.
The expectation, though, is that the number, if you like, of independent F terms is still going to blow up with the rank, with the number of Coulomb branch operators.
Yeah, and yet, I sort of suspect that there is probably some unexpected simplification. I should say, when we started trying to make these predictions, we didn't realize that all the higher derivative F terms were absent in rank 1. Like, that was a completely unexpected simplification. We didn't realize that until we were like 90% of the way through. It's a rather major thing to only notice at the last minute. So, my guess is that there will be some other sort of simplification. I don't know if this makes sense, but
this is part of your expectation that every extreme limit has some sort of simplification.
Well,
because here's another extreme limit. This is, I guess, a challenge then, is to go to very large rank superconformal.
Right. Well, then things would surely get more complicated. But I mean, I'd be happy to understand something about rank 2, really. And I suspect that something simple. I expect that it will be simpler than one expects, but I'm not sure exactly how.
Already in rank 1, you didn't even need those to get the leading term, no? The leading term just comes from the free part of the action, and that's it.
That's right. I mean, I guess fundamentally, I feel like there's no real reason why rank 1 should be so different from rank 2. There's nothing really fundamental about rank 1. So it would seem a little bit weird if rank 1 were so simple and rank 2 were really ungodly complicated.
Oh, sure. There's a big qualitative difference between rank 1 and higher ranks, which is that there's the U1R symmetry, which kind of acts not exactly transitively. Well, that in conformal theories, that together with the scale symmetry acts transitively on the Coulomb branch, but stops being true in higher ranks.
I realize, yeah, and and there's wall crossing and all sorts of complicated things. I agree. I mean, certainly more complicated things can happen, but just because rank 1 turned out to be a lot simpler than we initially anticipated, I don't want to jump to the conclusion that rank 2 is, impossibly complicated before actually checking. There may be some pleasant surprises there. I should say one other thing. One thing which we haven't done at all, which maybe would be a good idea, is Higgs branches, because then one has like higher dimensional vacuum manifolds, which are where there is a transitively acting symmetry, some sort of exotic global symmetry or something. So again,
the flavor symmetry in the SU2R isn't always transitive, right?
Right, but there
in
are
nice
many interesting.
situations, but often, I think even generically, it's not. Even on
Right,
these.
but there are many interesting conformal examples where it is.
Yeah.
So, it would be interesting to check out some of those. I mean, that might be easier than Coulomb branches at rank 2.